We've seen a number of techniques, some in previous lectures and some we've talked about in this lecture. We've seen the naive Bayes classifier fairly in detail. We've seen some probabilistic graphical models like Bayesian networks. We've seen linear regression in detail this time. We've also heard about logistic regression, neural networks, and support vector machines, at least as to what they are. And let's look at the problem and see which kind of techniques one would need to consider depending on the nature of the problem. We classify the problem in terms of the kind of features it has, whether they are numerical or categorical, that means numbers or classes, and the target variable, which is what we're trying to predict. We might be predicting a value, then it becomes a prediction problem where the value is numerical. We might be predicting a class, in which case it's a classification problem, which is part of learning theory. Techniques can be used interchangeably across these two different types of prediction. Based on the kinds of features, of course, some techniques are more applicable than others. So in the most straightforward case, if we have numerical features and a numerical target we want to predict, the correlation is stable and fairly linear, we'd use linear regression. Now, when I say stable and fairly linear, even in situations like this, one would still prefer to use linear regression rather than some complicated nonlinear function, because using higher order functions with say squares or cubes and sines and causes will tend to overfit the data and will not generalize to situations which may arise in the future. So right now you might have a great fit to the training data, but it really doesn't work in practice. So linear regressions is preferred unless you have some real reason to not use linear techniques. Similarly, even if your features are categorical and your target is numerical, you can still use linear regression, but you have to code the features. So if the feature, for example, takes 5 different values or 8 different values, you replace that feature with 8 categorical variables, binary ones taking 0 and 1, depending on which value, which category value that feature took. It's better to do with binary coding as opposed to, say, numerical coding, because there's no reason why red being coded as 5, blue being coded as 6, and green being coded as 7. There's no reason to believe that red and blue are closer than red and green. So using 5, 6, and 7 is misleading and can make the regression technique go haywire. So using 3 different features, each 0, 1, to figure out whether something is red, blue, or green is better than using numbers. When we have categorical variables and a numerical target, neural networks can also be used, just like they can be used for normal linear regression as well, but they have sort of waned in their popularity, except for certain situations which we'll talk about in the next section. Now let's come to the case where we have unstable or severely nonlinear situations, which might look something like this, as we've seen before. There's no way one can fit a straight line to this parabolic curve, and therefore it's better to use a neural network which has nonlinear elements, multi-level and hidden layers, so a more complicated function can be learned. At the same time, one is not presupposing that it's going to be a parabola, because that would be kind of counterproductive, because one is sort of presupposing the nature of f rather than letting a neural network with many different possibilities discover it. Next, we come to the classification situations where the target variable is categorical. Of course, when we have categorical features and categorical targets, we've seen how to use naive Bayes and other probabilistic graphical models. These days, SVMs, or support vector machines, are also very popular for even classification. Of course, for categorical variables, one does have to do feature coding to a certain extent. So we we do need to do the same trick that we did for categorical features in linear regression, because SVM essentially requires numerical inputs. Of course, if you have numerical inputs and categorical classification, SVMs are perfect. They are designed especially for those situations where you have unstable and severely nonlinear correlations, and that's what they essentially do very well. On the other hand, if you have fairly stable linear correlations and you do have a classification problem, then rather than using linear regression, as we have seen, one should use a logistic regression where one is bumping up or bumping down the difference from the separating line using the logistic function. So take a look at this table. It will guide you definitely in the problem set or the homework, the programming assignment for prediction. But in general also, it's something that you should learn something from. We have not covered many techniques here. We've only taken a very few techniques. Further, we've only talked about classification and prediction. Optimization, control, we haven't talked about those, and we won't have time to get into those in this course.